All right, here we go. Homework 12. This is the last one. Let's go ahead and get started. Problem number one. Simplify this uh, rational exponential equation. So one of the properties that we can use, and I like to write the properties in red, is that A over B, that doesn't look like an A, that looks like an alien. A over B to the M is equal to A to the M over B to the M. And A times B to the M is equal to A to the M, B to the M. Those are two of the big properties that we're using. So this becomes, this negative 3 is going to go to everything. So this is going to be 3 to the negative 3 times M. 4 times negative 3 is negative 12 over M. Negative 3 times negative 2 is 6. Okay. So a little bit of math. 3 to the negative third is 1 over 3 to the third. So that goes different color. So this goes down to the denominator. And so does this. But this combines with that. So all that stuff in the denominator, the numerator is 1. 1 over 3 cubed. 3 cubed is 27. And then m to the 12th times m to the 6th is m to the 18th. And that's my answer. We like problems like those. Those are pretty direct. The big thing is to know the application of your exponential functions, or your exponential properties. Okay. Whoa. Let's continue. Write the following as a radical expression. Remember, the top number is raised to the power. The bottom number is the index of the radical. So this is the 5th power of b to the 4th. Okay. Number 3. Write in simplified radical form with at most one radical. So you have to combine these. So I like to change these to fractional exponents. So this is y to the 1/6 times y to the 3/4. Properties of fraction is adding. Well, you add fractions if they have the same base and they're multiplied by each other. So y to the 1/6 plus 3 over 4. Now, I normally do not advocate this, but I think that you can see my calculator here. Let me make sure. Oh, you can't see the calculator here. Okay, let me change that so you can see the calculator. Stop sharing. I'm sure there's an easier way to do this. Okay, so this is the calculator, some calculator software I found, and this is a emulator of the TI-84 Plus. So this is what we have here. So I'm going to do 1/4 plus, what's this? 1/4, 1/6 plus 3/4. So 1/6 plus alpha y equals 2. That gives us fractions. Is it 3/4? Yeah, 3/4. 3/4. Enter. 11/12. So that gives us that. Let me see if I can do this a little bit easier. Okay, so this becomes, when we show this, is equal to y to the 11 over 12, which is the 12th root of y to the 11th. Okay, I have the calculator up here. I thought that it was a little easier to use it. Maybe not, but we'll just see then. Okay. So number 4, we have a graph here, and they want us to find out some information about it. So let's just zoom out so we can actually see all of this stuff. So this is a graph, certain things they want to know. So first, the function f is increasing over which intervals? The intervals are x values. Again, the intervals are x values. So from negative infinity to negative 9, this graph is increasing, which is what they asked. So increasing here. Then it goes down, and then from negative 6 to negative 2 is increasing. Okay, decreasing, decreasing. Then from 2 to 6 is increasing. Okay, let's keep going. And then from 9 to infinity is increasing. So that's that. So which x value, so moving on to B, at which x values is there a local minima? So minima, there are minimums or bottom, where it's the bottom of the hill at negative 6, at 2, and at 9. Okay. What is the sign of the leading coefficient of f? Is it positive or negative? Well, if you know anything about this, you know that positive, x goes to positive, it goes to positive infinity, negative goes to negative infinity. That is definitely a positive odd function. Or positive with an odd degree, rather. Right, positive with an odd degree, it's not odd. So which of the following is possibly a degree of f? So we look at the number of turns, and that is the minimum number of the minimum degree. So 1, 2, 3, 4, 5, 6. So 6 is the minimum degree, but it's odd. So that means that it is 7 and 9. We know it's odd because either both go to positive infinity or both go to negative infinity. Let's continue. 5, divide. Fun, right? So let's set it up. 3x plus 1 divide 6x cubed plus 17x squared plus 23x plus 8. What times 3x is equal to 6x cubed? That is 2x squared. So this becomes 6x cubed plus 2x squared. Whoa. In parentheses, put a minus sign in front of them. That's probably the most important part. Okay. 6x, that cancels, and it always will. 17x squared minus positive 2x squared is 15x squared. Bring down the plus 23x and repeat the process. What 3x times what is equal to 15x squared? Well, that's plus 5x. And you get 15x squared, and you get plus 5x, parenthesis, minus, the first number cancels per usual. 23 minus 5 is equal to 18. Positive 18. Plus 8. What times 3x is equal to 18x? That is 6. We get 18x plus 6, parenthesis minus. First number cancels, and 8 minus 6 is 2. So the quotient is 2x squared plus 5x plus 6, and the remainder is 2. I went through that kind of quickly. If you need me to do more on these, let me know. But I went through it quickly because it's pretty direct and straightforward. Let's continue. Past halfway there. Our function is a rational. The graph of rational function shown below, assume that all the asymptotes and intercepts are shown on the graph, has no holes. Where is the vertical asymptote? Vertical means up and down. That is at x is equal to 3. So x equals 3. Horizontal asymptote, that is horizontal. That is the line y is equal to 1. Those are the asymptotes. Okay, so actually bring this up. This is problem number 6. So let me bring up another screen so I can refer to it. Okay. All right. So domain, right, is an interval or union of intervals. So we know that x cannot equal 3. So for our domain, we have negative infinity to 3, union 3 to infinity. All right, in range, y cannot equal 1. So we have negative infinity to 1, union 1 to infinity. No positive infinity. All right, x-intercepts, there is 1 at 6. And y-intercepts, there is 1 at 2. All right. Okay. So for number 7, they want us to graph all asymptotes. So we have 3 asymptotes that we have. The first is the x asymptote, or the horizontal asymptote. That is looking at x plus 3 is equal to 0. I mean, x cannot equal negative 3. All right. So normally we would go for our vertical asymptote, but we notice that x squared is 1 degree. Well, x squared is 1 degree larger than x. So that means, that means we have a slant asymptote. So x plus 3, and we're going into x squared plus 7x minus 3, and we divide. X times x is x squared, doing it with x squared plus 3x minus 7x minus 3x is 4x minus 3. And you add what times x is 4x. 4 times x is 4x. 4 times 3 is 12. Negative 3 minus 12 is negative 15, but we don't need that. X plus 4 is our slant asymptote. So boom, boom. But this is supposed to be, actually it's supposed to be a dashed line for our asymptotes. So let's go ahead and do it right. Boom, boom, whoa. Let's try to do it right. That's it. That's close enough. Boom. That's what the asymptotes look like. Okay. Graph the rational function that. Now we're not going to ignore the fact that you can do this on your calculator, but we like to go ahead and factor these things anyway, because sometimes the x plus 2, x plus 4, because we see things like holes and things like that. Like we see things when we factor it all the way. So if I cancel these two out, I end up with the simplified function of negative 2 over x plus 2, with a hole at x is equal to negative 4. So I plug this in here. So do f of negative 4. Actually, I'll do f sub 1 of negative 4. F sub 1 will be this new function. So this is negative 2 over negative 4 plus 2, which is equal to negative 2 over negative 2, which is equal to 1. So at negative 4, comma 1, there is a hole. Okay, so new function, vertical asymptote, x is equal to negative 2, based upon what makes this equal to 0. Let's make this a little thicker, and let's make it red. I like having my asymptotes in red so I see them. I see negative 10. Yeah. Yeah, that's it. All right. There is no way for there's no x-intercept because our top can equal 0. Our horizontal asymptote, the degree of the top is less than the degree of the bottom. So that is y is equal to 0. All right. Now here's where I'm going to show you something on your calculator. Negative 2 over x plus 2. Let's do that. Nope. All right. Throw the calculator in. That's not what I asked you to present. Window, calculator, here we go. Okay. Y is equal to negative 2 over x plus 2. X plus 2. We graph it. Boom. This is roughly what our graph looks like. But that's not what we want to see. We want to see, let's see. I don't want to see that. I want to see my table. That's not it. So let's just do it the old-fashioned way. Table. So this table will give me all of my values. So I know that my asymptote is at negative 2. That's why there's an error there. But the reason why I did it is because if I go here, this gives me my x and y values for my function. So I know 0, -1 is 0, -1 is a point on my graph. What else? 0, -1, -1, -2, 3, 2. We know points on the graph. Okay, so let's go back and put these points on the graph so that we're able to use them. This helps you know where your graph is. Let's see. Can I can't change. I'm going to figure this out one day. All right. All right. So we knew that we had 0, -1, 0, -1, 1, what else? 1, -1, -2, -1, -2. Tell us what our graph is doing. -3, 2, and -4, 1. -3, 2. And 4, 1 we know is a hole, which it doesn't show the hole because I graphed it like that, but I already knew it was there. So the graph will look something roughly like this. Goes through here, goes through there like that. It doesn't do that little boom going out. All right, and then it's infinitely close. Turns the corner and does that. That's roughly what the graph looks like. So as you see, your graphic calculator does most of that for you. Okay. This is at 20 minutes, so I'm going to go ahead and stop this and then tackle the next 3 questions in the next part of this. I'll take a little 5-minute break.